Welcome back, everybody. Today we're going to talk about compound probability, which is the probability that is involved when you have multiple events. In addition to compound probability, we will also discuss independent and dependent events and how to determine if two events are independent or dependent. So what is compound probability? Well, compound probability comes into play anytime we have the combination of more than one event. When you're solving compound problems, you want to think in your head, if this happens and then that happens. So if the first event happens and then the next event happens. So you might be thinking, so what's the difference? I don't know what the difference is between compound events and what we did the day before with conditional probability and before that with just basic probability problems. What's the big deal? The big difference is that in the prior problems, when we worked on conditional probability and just basic probability, we were talking about a single event. If you recall, I suggested that no matter what the problem is, you take all of the items that you're working with, put them in a box, shake up the box, reach in and pick out one item, and then determine what the probability is of getting that one item. So some examples that we already worked on were like these, where the spinner randomly lands on an even or a red space. Those are two things, even or red, two conditions, but we're still only selecting one event. It's only one time. We're spinning the spinner one time. Well, we might roll a die and see if it lands on 6, the probability of getting a 6 on a single roll. Now what we're talking about are compound events. So we're talking about the probability of multiple events occurring. So it would be one thing and then another thing followed by another thing. So there's an order involved. An example of these might be selecting 3 red marbles out of a jar and the probability that you get all 3 marbles that are red. Or rolling 2 dice and getting double 6s. Now you have 2 different items that are involved. What's the probability of getting a 6 and then another 6? When we're solving compound probability problems, we can use something that we call the general multiplication rule. And the general multiplication rule states that we can take the probability of the first event and multiply that by the probability that the second event occurs. We could also go on and on to more than just 2 events. So we would continue times the probability that the third event occurs and so on. And when you're doing these problems, if you think about it in a sort of an order where you have a first event and then a second event, then what we need to take into account is, does the probability of the second event happening depend on the outcome of the first event? And if you recall, that's a form of conditional probability, and we're going to get into that in just a minute. Let's do some examples and it will be more obvious about what we're talking about. So in our first example, we want to find the probability that we roll double 6s if we roll 2 dice. So we could roll the dice at the same time, but to figure out the probability, it's usually easier to think of it as being one dice and then the other. So if you think if this happens and then that happens for all of these problems, we are much more likely to decide if we need to take into account some form of conditional probability on the second roll, or if that really doesn't come into play here. So one way we could figure out the probability of rolling double 6s is to list out all the possible outcomes and combinations. So if we consider these 2 different die, and in this case we could think of one being red and one being white, we could list all the possible ways that we could roll the 2 die. So we could get double ones, double twos, double threes, on to double sixes, and any possible combination thereof. So you'll see that there are 36 possible outcomes, and double sixes is just one of those. So we would have just this over here that I'm trying to highlight in yellow, not very well. But we would get double sixes would be one out of the 36 possible outcomes. Luckily, we don't have to always list out all the possible outcomes. We can use the general multiplication rule, which makes it much easier and time efficient and everything else. So in our example, what's the probability we roll double sixes? Well, we first need to figure out, well, what's the probability we roll a 6 on the first die? So we're thinking this and then that. So the first die, event A, would be 1 out of 6. And event B would be rolling the second die. So if we want to find the probability that both happen, we get a 6 and a 6, we can multiply the two probabilities together. So in this case, what I get on the first die doesn't have any impact on what I would roll on the second die. So these are actually what we call independent events. We're going to talk about that more in just a minute. So I can calculate that I get a probability of 1 out of 6 on the first die, and I get a probability of 1 out of 6 on the second die, and then I multiply those together. So I'll get my final answer is 1 out of 36, just like if we listed out all the possible outcomes, which is approximately 0.028 or about 0.03. In the last video lesson, we talked about conditional probability, and conditional probability comes into play here because when we're multiplying two events together, we really need to know if the outcome of the second event depends on the outcome of the first event. So we are considering our conditional probability if we have two events where event A is the first event and event B is the second one. We really need to consider, well, what's the probability of event B given that event A already happened? And we talked about this notation in the earlier video on conditional probability on our probability day 2. So this notation means the probability of event B given event A has happened. And so when we use the general multiplication rule, the formula, if you will, would be the probability of events A and B is equal to the probability of event A happening times the probability of event B happening, given that event A already happened. So you'll see this formula quite a bit. And this looks a little bit complicated, but really all that we're doing is taking into account the conditional probability of the second event. So when you're deciding if you need to use the conditional probability of the second event, you can look for words in the problem that say with replacement or without replacement. And sometimes the problem won't even say those words specifically, but you can think in your head, okay, am I using with replacement? Am I replacing the item and putting it back before I draw again? Or am I keeping the item outside the bag or the box or whatever we're working with and drawing a second time? So in your head, always think about with replacement or without replacement, because this will impact the probability of the second event happening. And we'll do an example to explain what we're talking about here. Let's look at example number 2. So if you recall from prior days when we've talked about probability, we always have lots of jars of marbles. So going back to our same jar of marbles we've worked with before, we have a jar here that has 14 red marbles, 8 green marbles, and 12 blue marbles. So the question is, if we select 3 marbles from the jar, what is the probability that all 3 marbles are red? So before we even start with this problem, we want to think about, is this a with replacement or without replacement problem? And it doesn't clearly say those specific words in the problem, but if we read it again, it's understood that we're going to select 3 marbles and nothing says anything about putting the marbles back in the jar. So we're going to assume that we're going to select 1 marble, set it aside, select another marble, set it aside, and then select the 3rd marble and set it aside. So this problem would be without replacement. So in this case, we need to figure out the probability of selecting our first red marble. So very first thing we need to do is add up all the marbles in the jar, and we get 34 marbles. So when we select the first marble, we're going to get a probability of 14 out of 34 because there are 14 red marbles out of 34 in the jar. Now we're going to keep that red marble outside the jar. So we only have 33 marbles left in the jar, and we already have 1 red marble. So it's going to be 13 out of 33 for the second red marble. And then when we go to select the 3rd red marble, now we have the first and second red marbles are already outside of the jar. So we only have 32 marbles left in the jar, which leaves us 12 out of 32. Now we can take each of those probabilities of the first event, the second event, and then the 3rd event and multiply those together to get a probability of 0.06. So a couple of things before we go any further. When you're dealing with problems like this, first of all, unlike what the Rolling Stones song says, you always get what you want in probability. So if you're asked to find the probability of getting all 3 red marbles, assume that you get a red marble, and then a red marble, and then a red marble. Because in probability, we always get what we want when we're trying to figure this out. And secondly, when you're multiplying in your calculator, if you're going to set these problems up to multiply fractions in your calculator, make sure that you put your fractions in parentheses, because if you don't, your calculator is going to give you a wacky answer. So the other way to do this in your calculator would be to multiply the 3 numbers in the numerator together, hit enter, and then you're going to divide by these 3 numbers multiplied together. So you would want to put these in parentheses. The other thing is that you do not want to simplify your fraction. So 14 out of 34, for example, could be simplified, but don't simplify your fraction until the very end of the problem. So if I were going to multiply this out and get a fraction answer, I would get this ugly answer of 91 all over 1,496, which isn't really a very practical way to look at things. So usually with types of problems like this, we usually give a decimal answer, in this case 0.06. Now consider the difference when we look at part B. So on part B now it's saying if we select 3 red marbles from the jar, but we're replacing the marble after each draw. So we still want to get the probability that all 3 are red, but in this case, this is a with replacement problem. So when we do this, the probability of each draw does not change because we're putting the red marble back in the jar each time. So in this case, the probability each time is 14 out of 34. And then when we multiply those together, we would get 0.07. So we have a greater chance of getting 3 red marbles, or a marble 3 different times, is how to think of this problem really, if we've replaced it each time, than we do if we're taking a marble out of the jar each time, which makes sense logically if you think about it. When you have problems like this, when you have with replacement, you can take the probability of the event, drawing a red marble, 14 out of 34, and you'll see it sometimes written like this, where it's 14 out of 34 raised to the third power. In this case, 3, the number 3 is the number of marbles we're selecting from the jar. The probability doesn't change on each draw, so that is why we can say 14 out of 34 raised to the third power, and we get approximately 0.07. So the last thing we want to talk about today are independent versus dependent events. And two events are said to be independent if the outcome of the first event does not influence the outcome of the second event. For example, in the dice problem that we did earlier, when you roll the first die and get a number, that doesn't have any impact on what kind of outcome you're going to get on the second die. Same with flipping a coin. If I flip a coin over and over and over, whatever I get on the first flip is not going to influence the outcome of subsequent flips. However, in the marble problem, when we did not replace the marble, the second event, the second marble drawing, depends on what I got on the first event. So when we write this, you'll remember that this notation refers to conditional probability. We're saying the probability of B, if B is our second event here, so the probability of B is equal to the probability of B given event A already happened. If those two things are equal, the two events, A and B, are independent because B does not depend on event A. If those are not equal, then event A influences the outcome of event B, and then we say the two events are dependent. So you will be asked to determine if two events, events A and B, are independent or dependent. So when you're doing that, there are actually two ways that you can check and justify your answer. The first one is you calculate the probability of event B happening all by itself if event A isn't even involved. So find the probability of event B and compare that to the conditional probability of event B given that event A happens. If those two are equal, then the events are independent. If they're not equal, the events are dependent. The other way to do this is look at the probability of event A by itself and the probability of event B by itself. And if you multiply those two things together and you get the probability of events A and B happening, then the two events are independent. If probability of A times the probability of B does not equal the probability of A and B, then they would be dependent. So when you do these problems, and we'll do an example here, you are going to calculate these different probabilities and then compare them to each other to determine if an event is independent or dependent. So in our third example, we are working with a table that we worked with earlier about party invitations. So we have invitations that were sent to 144 students, and we're trying to decide if the two events attending the party, so party attendance, and passing your classes, or in other words, how are you doing in your grades in your school, are those two different events independent or dependent? So it says, determine if the events are independent, justify our answer. So the first way we're going to do this is look at the probability that somebody will attend the party. So again, now we're just talking about reaching in this box of students, pulling one student out at random. What is the probability that they will attend the party? So in this case, we're looking at 96 people out of 144 will attend the party, and that's about 0.67. Now we want to compare that to the probability that they attend the party given that they're passing. So we're comparing this to the conditional probability, which is 85 out of 100, so which is, of course, 0.85. So we want to see if those two things are equal. Obviously, they are not equal in this case. So we say that the two events are dependent, which logically makes sense in this case also. So we said in prior examples that if you're able to attend the party, that might depend on whether you are passing your classes in school. I will caution you, though, you want to be careful not to just use logic in these problems, because a lot of times it's kind of like those word problems you get with, like, you go to the store and you want to purchase 1,000 watermelons, and like, who the heck is ever going to do that? Same thing with this. You don't want to use logic in these problems to determine if events are independent or dependent. You want to justify your answer with math. So this is the first way to justify your answer. You're comparing the probability of attending to the probability of attending given that you're passing. When you do these problems, make sure that when you're looking at the individual probability of attending, you want to look at your conditional probability in the same order. So you would have attend and then attend given the other item. The second way to check this problem is to look at the probability of A times the probability of B and see if that is equal to the probability of A and B. So in this case, probability of A, we'll say that that's the probability of attending, and so that would be 96 out of the 144 students. And then the probability of B, we'll say that's the other one, so that's the probability of passing. We're going to look at the totals there. So 100 out of 144, which is about 0.69. And then we want to look at the probability of attending and passing. And if you recall, when we did this before, we looked at where those two intersect. So passing and attend is 85 out of 144, which is about 0.59. When we multiply these two numbers together, 0.67 times 0.69, we get 0.46. Well, 0.46 definitely is not equal to this 0.59, which we know is the probability of both events occurring because it's given to us. So these events, we would say, are dependent. If they're equal to each other, we would say they're independent. If they're not equal, they are dependent. And regardless of the way that you solve the problem, whether you're using this method or the conditional probability method that we just did, you will always get the same result. So if you're showing using this method that the events are dependent, using the other method, we will also get a result that the events are dependent. And in the problems that you're given, it will usually ask you to use one method or the other to solve the problem. Okay, so that sums everything up that we're going to do today. And look forward to having you back next time, where we'll do some more challenge problems and some problems with working backwards with probability problems. Thanks, and have a great day.